Thank you to all the organizers for giving a chance to present our work. And my respects and my for Professor T.V. Ramakrishnan. Now, I have been placed in a bit of a weird, between Senthil and lunch is the worst place probably to be giving the talk, but I'll try my best so that you stay until the end of the talk. Okay, so I'll talk to you today about Andreev versus tunneling spectroscopy for flatband superconductors. And before I start my own talk, a very happy 85th to TVR, and we hope that we benefit from all your wisdom in the years to come. With that, let me get back to my talk. This work has been done with Shayok Biswas, who is a student at Ohio State University. Shayok is here, and he knows more of the details of the work. So if you have questions, please catch him. Saurabh Suman is a graduate student at TIFR. Mohit has been involved in the work from the beginning. So this is Shayok, Saurabh, and Mohit, and me. And so it has recently come out in this paper. That will be the basis of the talk. Okay, so let's see. So Senthil had already talked, and many others have talked about twisted bilayer graphene or Moiré systems. The basic idea is you take a 2D sheet of material, you take another 2D sheet of material, maybe the same, maybe slightly different, and then you twist slightly the crystal axis of one with respect to other as you press them down. And this, when you do that, you will see that these two lines are slightly twisted with respect to each other. And if you look at this pattern, you will see that you create essentially quasi-periodic patterns on a much, much longer length scales, especially if the twist angles are small. And also, these patterns are very sensitive to the twist angle, so that gives you a way to access and change properties of these materials by twisting it by different angles. Okay, the most celebrated one is the Moiré twisted bilayer graphene, where you take basically one layer of graphene, another layer of graphene, and put on top of each other. In this case, it turned out that in 2011, before the modern experiments were there, Bestridzer and MacDonald had looked at this question and tried to ask what would be the band structure of these systems. And here is a calculation of the band structure, I think, at 5 degrees. And here is a calculation of the band structure at 1.05 degrees. And what you need to see is that this blue band, which was about 500 millielectron volt, has essentially collapsed to something which you can hardly see in this. Okay, so there are these magic angles, which is around 1.08 degree, where you end up having a very, very low bandwidth of the system. In fact, if we just push this out, bring it up, you will see that in the non-interacting calculation, the bandwidth is essentially about 2 millielectron volt, 3 millielectron volt. With interactions, experiments probably see around 10 millielectron volt, 15 millielectron volt. But this, of course, is a completely new scale for doing condensed matter. I mean, normally, you're not used to looking at bandwidths of 10 millielectron volt in standard condensed matter. So we get this almost flat band at magic angle of 1.08 degree. And if you have a flat band, of course, you would expect strong correlation. Your kinetic energy has been kind of quenched. And you would expect a lot of different kinds of maybe correlated states. And many of them show up. Some of the more exotics Senthil talked about a little bit ago. I will talk to you about something which is simpler, or at least more straightforward. And what happens is when you try to fill up these bands have a degeneracy of 4. There is a valley and there's a spin. And so if you go to a filling of -2, that's in the non-interacting picture, you are filling up basically half of the degrees of freedom, or emptying out half of the degrees of freedom in this band. And at that point, band theory should have given you a metal, but you do get an insulating behavior. Mott, people are probably not so sure whether it's Mott physics, some other physics, but you do get a correlated insulator at half filling. And you dope away from this, you basically end up getting superconductivity. Okay, so this was seen in 2018, and by now there are multiple, many experiments which have seen superconductivity in this flat band superconductors. Okay, so you have superconductivity in this. The next thing I want to point out is that by now, we are not looking at a one single material. This is a paper which came out in 2022, where essentially you look at different layers, number of layers of graphene you put in, and you twist them in different ways. And all of them, there is MATBG, there is twisted tri-layer, which is 3 layers, 4 layers, and 5 layers. And all of them kind of show superconductivity in some doping regime, some particular magic angle, and some low temperatures. And all of these things, what they have in common is that they have a flat band. Of course, the details of the band structures and so on are different in each case. Okay. So we can look at more rhombohedral tri-layer graphene. Again, this is not a Moira material, but again, shows superconductivity and a flat band. You have bilayer graphene, which has approximately with WSE2, that also shows a flat band and a superconductor. And there are more, which I'm not talking. So the point being that there is this general class of now superconductors, which are all superconductors which came out of systems which had a very flat band or very low kinetic energy in them to start with. Okay, so now some key unanswered questions in this. There are many, but focusing on the superconducting phase, one of the key unanswered questions is what is the symmetry of the Cooper pairing in these systems? And there's some hints, but there is no clear idea or no smoking gun evidence for what the symmetry of the Cooper pairing is. And the symmetry, of course, often dictates the mechanisms you would think about how the Cooper pairing arises. So mechanism and symmetry are sort of not one-to-one, but they are related to each other. They would influence one another. And the second question, of course, is this superconductor essentially a BCS superconductor, a mean field superconductor, or is it a very strongly interacting superconductor? Going back to the days when I started my PhD, with the epitome of a strongly interacting superconductor would be the cuprate. And of course, weirdly, this phase diagram has some similarities, although probably it's not many of the details are different. However, question still remains, do you have BCS as a good description, or do we have very strongly fluctuating superconductors where we would need to think of strong correlations as an intrinsic part of this? We can also ask, are these correlated insulating states important for understanding the superconductivity, or are they not? Because there are experiments where the dome of the superconductor, depending on what you do in the material, seems to shift from near the insulator to slightly away, and sometimes much away. So again, question that is not completely clear is just empirically is it tied to the insulator, or you can move it around and this insulator is not so important for understanding the superconductor. And of course, the final question is, I showed you a bunch of materials. Is the superconductivity in these different compounds coming from the same physics? Are there different classifications, different things happening? Experimentally, we don't know enough to make that kind of a statement. Okay, so these are some key unanswered questions. And part of the problem, of course, is that these are very low temperature. These are almost 2D systems, and they are covered. So a lot of standard condensed matter techniques that we would normally use to probe these systems are not available or not very easily available for these systems. So having said all this, having set this sort of background, I will try to focus on one set of experiments I will try to show you that the standard way of understanding these experiments are probably not so kosher. And then they will throw up a puzzle, and we will try to answer the puzzle. And in the process, we will see that when you do these experiments on flat band superconductors, you have to be careful about how you analyze these experiments vis-a-vis when you would have done the similar experiments on a standard superconductor. Okay, so what's the experiment? The experiment that I want to talk to you about was done in 2021 by Yali Yazda and his group. There's similar work on twisted tri-layer graphene. This is on twisted bilayer graphene. And so what is the experiment? There were two sets of experiment. One is that you bring a STM tip and you look for the tunneling conductance through an STM tip. Here is the data. You basically see that you have a kind of a V-shaped gap, and then you have a sort of a superconducting coherence peak, and then you have something that goes, goes to some high bias conductance. Okay, so this, of course, is a typical behavior of maybe a nodal superconductors. And you can figure out the superconducting scale by essentially looking at where the peak is occurring. And out of that, you will get a scale which will give you about 0.9 millielectron volt. I mean, you can change temperature, the answers would change. This is at a particular temperature, at a particular doping. And then what you can do is you can crash the tip into the sample. So the tip is now touching the sample. This is normally what people would call point contract Andreev reflection, but essentially Andreev spectroscopy. And then you see this sort of a figure. You see an excess conductance and at low bias voltages. This is coming, the fact that you almost see a gap is because this part is dominated by electrons trying to tunnel, and you don't get enough states if you are in the gap, within the gap at low bias. Here, this is supposed to be dominated by the standard law would be that what you are seeing is Cooper pairs tunneling, which can tunnel at zero densities and so on. And that's what is giving rise to the excess conductance here. However, if you fit the data and you extract a gap scale, you'll see the gap scale that you will get here is about 0.3 millielectron volt. So there's about a factor of 3 to 4. So if you just look at the two data on the same material, you have put your STM above or you have crashed, and you get a spectroscopic or an energy scale out of it, but there's a feature, and the feature is a factor of 4 off in the Andreev versus the tunneling spectroscopy. Okay, so that throws up a puzzle. Why do you have two scales in your problem? What are the two scales? Why does Andreev and super tunneling spectroscopy not show you the same set of scales? Okay, that's essentially, you can write it down here. Why are there two distinct scales? So remember, it's not that the Andreev shows one scale and the tunnel, both of them show a single scale, except the numbers don't match with each other. This is a data where they are basically taking the tunneling tip closer and closer and closer, and you can see that there's this new scale appearing, where this is at when you are doing a STM-like measurement far away from the sample. Okay, so you're going from here to there. Okay, so next question is, okay, so maybe we go back to what we had learned about cuprates and so on, and we can say that, oh, maybe this is something that has been not quite said very clearly, but has been a sort of a lore in the literature that, the Andreev measurements must be looking at the Cooper pair or the coherence scale, if you define it in some way. And so maybe what the Andreev is seeing is a coherence scale or a superconducting gap, whereas when you are doing the STM, you are just looking at a single particle gap, or what you would call the pseudo gap. Okay, so that's, for example, Deutscher in the context of cuprates had tried to ask similar questions and so on and so forth. Okay, so that's one question. Maybe the answer is that your superconductor is very strongly interacting, it shows pseudo gap physics, there are two different scales, one for forming the superconducting coherence, one for some, this is without telling where the pseudogap comes from. There's another scale, maybe formation of Cooper pairs, maybe something else. And what you are doing in these two experiments is probably you are looking at the two different scales. That's one possible answer to the question. Yeah.
Can you remind us what C when you crash it in the same way?
In the same way, there are not that many. When you crash into, never been done. I don't.
Grad students must have crashed it many times.
They were chided by the Okay. And then the third question is that why is this scale going away when I go to the tunneling spectra? The scale just disappears when I go. So why is the I mean, normally, if I think of a tunneling spectra, in a standard superconductor, I see the superconducting gap in a tunneling spectra. If this is the superconducting scale, then we have this weird thing that I go to the tunneling limit, I have no evidence of the superconducting scale in my data. Okay, and so this puzzle is what we wanted to look at and try to understand. And this is what I'm going to talk to you about. What are the scales and why? How should we understand this? To do that, maybe it's useful to understand how this junction conductances are understood within the standard BCS-like superconductors. This is done by what is known as the Blonder-Klappwijk-Tinkham theory. It was done in 1982. And the way you think of it is you think of a very ultra-thin junction between the metal and the superconductor, and you model the junction as if the junction is giving you a scattering potential, a localized scattering potential, V. And then junctions are characterized by this dimensionless parameter Z, which is V over H bar VF. So small z would mean you have almost no scattering. It's almost a ballistic junction. Things can go through. And a high z would be a very reflective junction, which would have very high resistance and so on and so forth. Okay? And the idea in general is when you basically have an electron which is incident, it can get reflected. But because you have a superconductor on the other side, it can also get retroreflected as a whole with a downspin. And then you can have basically two quasiparticles propagate. If you are above the gap, and if you are below the gap, you will form two quasiparticles locally, which will die down into essentially a Cooper pair, which will now propagate into this. Okay? And the idea usually thought of is that if you are crashing the tip, you are in the low z limit, you are forming a contact with very low resistance. It's the Andreev limit. And if you're doing STM, you have vacuum or air, so basically you are in the high z limit. So one way, the standard way people would think of it is basically increasing z from 0 to infinity as you are going, or if you were thinking of going down in this with the STM tip, that's one way to think of it. And you basically, if it's a main field theory, you can write down wave functions. It's basically treat this as a scattering problem, and you solve the scattering problem using wave functions and standard boundary conditions. And again, you have an incident electron, a reflected electron, a retroreflected hole, and then you can construct the conductance out of this reflection and Andreev reflection coefficients. If you do this, and you ask what should you see if you go from here to there, this is just standard mean field theory. If you had a S-wave superconductor, everything is gapped. This is answers at 0 temperature. You should, in this limit, you just look at the single particle density of states, nothing here, then you get the peak around the gap edge, and then you go. If it's a D wave, for example, then of course you will see a V-shaped curve, and then you will see a peak, coherence peak, and then you'll go. If you go to this limit where you have a ballistic junction, you see this excess conductance, and for a S-wave, there's a famous factor of 2 between the normal state and this conductance. It remains there till you hit the gap, superconducting gap, and then you fall apart. Okay? If you are D wave, you come down, and then again, you will basically go here. But if you look at this scale or the point of inflection, you'll essentially see the same scale. Not surprising. BCS theory essentially has one scale in the problem. So you should not be surprised that you see the same energy scale in the problem. So if you were to go and explain that data, you would basically need something more than a single scale in the problem. If you want to say that, oh, maybe it's pseudo gap, etc. So you need to write down a theory which allows you to do the same problem, but without using wave functions or mean field theory. Okay. And the way to do this is to solve the same scattering problem by using Green's function techniques. So because you will be at a non-equilibrium with a current flowing through, you need to use what is known as Schwinger-Keldysh Green's functions. So you think of a bulk Hamiltonian for the metal, a bulk Hamiltonian for the superconductor. And the idea is, instead of specifying what the bulk Hamiltonian is, you specify that there's a bulk Green's function. Okay? So you're not going to make an assumption about what is the structure of the Green's function, other than that it has a 2×2 Nambu structure, because you ultimately want to describe superconductivity. But modulo that these are 2×2 matrices and has standard retarded Green's function properties, you will not make any assumption about what kind of Green's functions you are putting in there. You will think of the tunneling as an effective tunneling between the metal and the superconductor given by scale gamma. There have been papers before. Senthil had actually done some of the work here, and Cuevas and others before in a very similar fashion, and we will try to point out. So then you solve the problem. You say that, okay, there are these two bulk Green's function, and there is a coupling between these two. Can I now solve the problem? And the problem is basically, you write down, I'm not giving you all the details, but the ultimate answer is that you can write down the conductance in terms of some complicated objects. The object that you ultimately wrote it down in terms is simply a momentum integrated Green's function. Okay, so you give me a bulk Green's function without telling me, exact form. I can put it in the formula, and this should give me the G of V. Okay, this is kind of what comes out of all the calculation. So the point of doing this is that you can go back and you can ask, can I match this with my wave function-like approach, at least for the BCS limit? Okay, and turns out that while you are looking at this as a scattering potential, you are looking at Green's function approaches as a hopping. You can define a dimensionless hopping, gamma tilde, and then you can just say, forget about the superconductors, let's put two metals, and let's assume that this BTK way of doing it and the Green's function way of doing it must give me the same answer. After all, it's two free fermions. There's no reason the wave function and the Green's function approach should give me different answers. And then you will basically see that this gamma tilde can be related to Z like this. So essentially, if you are in the tunneling limit or the very high barrier limit, your gamma tilde is 0. If you are in the ballistic limit or no scattering potential limit, your gamma tilde is 1. Okay, and then you can do a dictionary which runs between this. The good thing about this is you give me your Green's function, I still do my G of V, but I can still talk of a junction with a particular Z, because that's what experimentalists always characterize their junctions by a particular Z. So, it allows me to talk about a particular junction with a Z. What I would do is there are some issues about doing it for unconventional superconductors where you have to remember that there are some boundary effects that you have to take carefully. Let's not go through them. We can talk about it. So what has this brought us? This has brought us a few things. You can do self-energy corrections. In principle, you can think of Eliashberg, pseudogap physics. Maybe you have an underlying quantum phase transition, multiband effects, BCS-BEC crossover. You are writing your answer in terms of measurable spectral functions because you are looking at the retarded Green's functions. And then you can do a comparison with experiments, etc. So the formula in general, other than this subspace Green's function thing, is essentially similar to this Central's formula or Kuiper's, but it has a much simpler thing written in terms of measurable Green's function, that's all. Okay, so if that is true, let's see what, can we see these different energy scales? Let me give you the answers. The first answer is no. Whether Andreev, can we interpret this as pseudo gap and superconducting gap? The answer would be no. How should we interpret the point contact data? Not in the same way as conventional superconductors. And what are the two energy scales seen in the experiments? And I'll try to argue that this is about Andreev bound states, and this gives us more evidence that what we have is a nodal superconductor than that. And these are some other papers which have been looking at other aspects of the tunneling in this modern superconductors. Okay, so let's look at the pseudogap physics. So what we will do is, pseudogap for us is essentially a separation of low energy spectral weight in the normal state. And rather than doing a theory of the pseudogap, we will just put phenomenological Green's function, motivated phenomenological Green's functions, and see what comes out of them. So the first model is essentially Green's function where you separate out that there is a superconducting scale delta, and there is a pseudogap scale EPG, and the overall energy gap, these two things add in quadrature to give you the single particle gap. If you look at this is a calculation at small gamma, so the STM-like spectra, and you will see that only the single particle gap is showing up. The superconducting scale does not show up in this case. You look at this in the other limit when gamma tilde is 1, you will see excess conductance, but you will see, again, things happening only at the single particle energy gap scale. Delta and EPG do not show up as in none of the limits, they show up as different scales. And more importantly, both limits see the same spectral scales in the problem. Okay, you can do it for more complicated models of pseudogap where you think of there's some soft pseudogap where there's some underlying density, background normal state density of states which has a soft gap, and then you put on a superconductivity on top of this. Once again, you will first see the first statement is in the tunneling limit, the superconducting scale shows up, which did not show up if you try to think of the experimental data in terms of a superconducting gap and a pseudogap. And then in both cases, once again, you see in this case, both scales essentially show up in these two things. So the net idea out of this is you cannot interpret your observed data in terms of a pseudogap and a superconducting gap. It's not going to give you, the data does not, and the theory doesn't work out. Okay, so having said that we can't interpret this as a pseudogap and a superconducting gap, let's ask how can we think about at least the Andreev data? And there is this idea that if you have two metals even with different dispersion and you create a junction, okay, and you have no microscopic potential, it's a completely nominally ballistic junction somehow you have created. The simple fact that the dispersions are different will mean that particles cannot conserve both energy and momenta, and as a result, as they go from one medium to another, they'll be reflected. I mean, in other ways of thinking about it, you would think of it more or less like an impedance mismatch, creating reflections and so on and so forth. Okay, so effectively, just the fact that the dispersions are different for metals, that means Fermi velocities don't match, would give rise to a junction potential. You can look at what that effective junction potential is, do some theory, you will see that the effective junction potential is whatever you did, effective Z, plus an extra term 1 minus alpha whole square over 4 alpha. Alpha is the ratio of the velocity mismatches, okay? And if you ask what about the Green's function, your gamma tilde alpha will get related to the Z alpha, Z effective and not to the usual Z. Okay. One small point here is that this actually comes out of the Green's function calculations, that in an interacting system, you can think of a bare band structure Fermi velocity. You can think of a Fermi velocity corrected by the exchange-like corrections or momentum dependence of the self-energy. And you have the full Fermi velocity, which also requires the quasi-particle residue. And the analysis shows that Z effective, what enters is the VF and not VF star. So somehow the frequency-dependent renormalizations, or renormalizations of VF that comes from frequency dependence of self-energies are not going to be important for you. However, if you have exchange or bare band structure differences, those are what you should actually look at. Okay. Again, earlier was done by Nogiers and Deutscher in some slightly more ad hoc way. Or yeah, fine. So what we realize out of all this is that it's impossible to reach the Andreev limit for flat band superconductors, because this is a flat band, your tip is a metal, there's a huge mismatch of Fermi velocities. So even when you're crashing your tip, you are effectively at a high Z barrier potential. So you cannot interpret it as just Andreev reflection like that. And so effectively both experiments see some sort of a single particle density of states. Okay, so the question then is, why do they see something different? And the idea is, when you crash, you actually create a real physical boundary between the metal and the superconductor, whereas when you are hovering above with your STM, there's no physical boundary created in the superconductor. And if you have a nodal superconductor where your order parameter changes sign, it's known from way back that you can get Andreev bound states if you create a sharp boundary in a D-wave superconductor. Okay, so the claim is, what is happening here is when you are crashing, roughly speaking, you are creating a boundary. There's an Andreev bound state, and the density of states you are seeing should include the Andreev bound state, whereas in the other case, you are just looking at the bulk density of states, so you are not seeing anything. Okay, so you can do, again, similar calculations, but now with the circular geometry. Again, since strong correlations are not what we are after, we can go back to a BTK-like or BDG-like analysis and solve the answers in terms of boundary conditions and so on. You can calculate for each angular momentum, you are pushing in electrons with a particular angular momentum, and then for that there is a conductance, and then you would have to sum over all these L naughts. You can cut it off at plus minus KFR, and that gives you some answer. And just as a zeroth order understanding, if you look at the high bias conductance, your high bias conductance now gets this number of channels, which is 2 KFR plus 1. There is a Fermi VF mismatch. If you take the standard answer, depending on what you take, this Fermi's velocity mismatch will go between 0.01 and 0.25. This is from experiments. So your KFS are, if I just take that at the large values, these are about 1 to 10. So these are not literally point contacts. You have a largish surface that you would have to look at. You do the calculation, we're done almost. We do the calculation. What you see is that if your KFR is large, you essentially see an answer which is for a planar junction, but averaged over the angle of the planar junction and the axis of the superconductor. But what is more interesting is, even if I go to KFSR of 1, you will see that there is still a pileup of the density of states due to this bound state. And this is what the experiments are actually seeing. That's why they're seeing a different scale. The different scale is simply the scale over which the density of states of the Andreev bound state is coming down. There is more evidence in other, for example, there is evidence for linear temperature dependence of superfluid stiffness, which hint that you would probably have a nodal superconductor. And the claim is that this itself is actually showing you Andreev bound states, and hence giving you more evidence that you are actually looking at a nodal superconductor. Okay, so let me skip this and go to my summary because I'm almost out of time. STM and Picker measurements on MATVG show different energy scales. They cannot be interpreted as a pseudogap and a superconducting gap. So you get this out of some Green's function formalism of conductance. And then for the flat band superconductors, and this is the important thing, that both the STM and the point contact is measuring your density of states. Both are at very high, highly reflective limit. And the different scales are due to Andreev bound state formed in junctions with the nodal superconductors. And these are the papers that has this. I'll stop here and take any questions that you have.
Thanks, Rajdeep. Questions?
Yeah.
Yeah, so I have a question. So in the D-wave superconductor, at the transparent limit, at Z0, so why don't you see a perfect 2 in the conductance? Because apart from the insulator, I don't see any scattering there.
No, so what happens is the D-wave see, you have a junction, so Ky is conserved, okay? So at a given Ky, when you are coming, okay, the D-wave delta is, when I'm writing delta naught, it's the antinodal or the highest gap, right? I have things which is at all sorts of gap. So one way of looking at why it is coming down, you just do it over different, for some angles, what is happening is that you are essentially above the corresponding gap. For some angles, you are below. So if you do that averaging, it will give you that curve. So that's why it doesn't remain fixed. It's roughly, you can think of fixed for certain angles where the gap, I'm below the gap, and for certain other angles, I'm just above the gap. So I'll fall down.
So also I have last question. How I do not understand how the pseudo gap arises, EPG.
You don't understand means you don't understand where it comes from?
Yes.
No, so we didn't say anything about where it comes from. The whole idea was not to wade into a microscopic theory of pseudo gap, but to show that if you have two scales in your problem, one giving you the order parameter and one giving you the energy gap, which is what you think of, okay, at bay. There are physical ways to motivate what I have written down. So you can think of maybe, the order parameter has lots of phase fluctuations, local phase fluctuations. If you average over them, the order parameter has gone down, whereas the gap which looks at mod square doesn't see that phase fluctuation. So I can hand wave and motivate that Green's function. But the whole idea was to put in a reasonable form of a Green's function with two scales and show that, you're not going to see the two different scales in this. So I have not given you a microscopic theory of why the pseudo gap happens. I have not gone into that at all.
Rajdeep,
Yeah.
I have just a question about your bilayer versus multi-layer graphene when you have. Is there a difference in their superconducting properties? They also superconductivity, but is there a difference? Because other than the flat band, I think there are many bands which are at the neighborhood, which are different between bilayer
Yeah,
and
sure.
multi-layer.
Point is, I don't think people have looked at all sorts of details for, so here, what they have looked at is you see the superconductivity and you see it more or less happening at similar temperatures. For tri-layer versus bilayer, people have looked at a little bit. For example, tri-layer, people see that if you look at as a function of magnetic field, you can violate the what is called the Pauli limit, probably indicator. In a standard BCS theory, you would take it as an indicator that you probably don't have a singlet superconductor and so on. And however, in bilayer graphene, you more or less see something which is within the Pauli limit. How much you should trust Pauli limits in this complicated, that's a question which is a complicated question.
Thank you, Rajdeep, for a nice talk. I may have missed, you may have said this. So you have this crash situation, right? So there's a length scale. I just wanted to know what is that length scale compared to the coherence length? You have to make some assumption about that?
So what we did was that, yes, in a normal case, you would worry about that because you are worried about proximity effects going into the metal, maybe on the scale of the coherence length. the way these things are done, you are basically assuming that the length scale is, I mean, proximity effects are not important.
No,
Or-
no, I'm sort of thinking in terms of, if you're thinking in terms of Cooper pair tunneling, if you're coherent, if you're large Cooper pairs compared to the size of your.
So in that sense, you have met that, that is the junction scale, right?
Right.
That's a scale of the junction.
The circle
Of the
boundary condition you put.
not the radius of the circle, but that's actually the thickness of that line, ring, that is what you are worried about. Because, are you worried about Cooper pairs tunneling inside?
No, no, you had that picture, right? You put boundary condition on that.
So
the
Cooper
radius
pairs
of
are
the-
outside.
Right, so what's the radius of that compared to the coherence length of the superconductor?
So here, I think in actual systems, you don't know how big the circle is once you crash. But if you take KFR to be order 1, your delta is roughly speaking somewhere, it's about 0.3 Kelvin. Fermi energies are maybe 10 Kelvin. So that gives you a sort of scale that coherence length is maybe 3, 4.
Oh, that's 5 nanometers.
Yeah.
So
No, he's
these
asking
are-
the coherence length is also of that
these are
order.
like type 2 superconductors, these things?
Sorry. Yeah. No, no, it's not microns. It's a few nanometers.
What do we know about the superconductors? Is it a type 2 superconductor?
Yeah.
It is.
2D. It's a 2D, so it should be extremely tight too. Yeah, so 2 or 3 lattice spacings of the Moire. Yeah, Moire lattice spacing. 10 nanometers, 14 nanometers. Yeah.
Noise in this system for these two extreme cases, Z0 and Z infinity, will that capture some signature of this different scale?
Possibly. Different scale, I'm not so sure, because noise, yeah, I mean, here when you are doing this, you are assuming that, all the voltage drop is just happening across the junction. And once you are in the bulk, essentially nothing is happening. You're just basically tunneling all the way through ballistically. If you do noise, I think you will also have to think about the bulk. Yes, but we argued that it's no longer Andreev. It's not Andreev in either case. You can find some signature, but what I'm trying to say, because of the Fermi velocity mismatch, your effective Z would be at a large Z, right? So then you're asking, if I have a large Z, but I have a bound state, will I see that noise? And the answer is yes. If you do that, you will see that extra noise coming from the bound state. And that's, whether you can pick it up, I don't know. Yeah.
Okay, let's stop at this question. Let's thank Rajdeep once more.
Yeah.